All right. First, I want to make some announcements before I even talk about the homework or ask about the homework. I may be traveling over the next couple weeks. I don't know what that's going to look like. It's for work, and it could mean that I have to post lectures rather than being here. So I hope that doesn't happen because I gave them my availability and none of it was during the week, but I'm just not sure, so I want to let everybody know now that that's a possibility. Outside of that, I guess people can't find my office hours posted anywhere because I still have people asking me when my office hours are. So right on the course webpage, guys, 12 to 1. Mondays and Wednesdays. So for anybody who doesn't know when my office hours are, here they are. I specifically have the gap before this class so that I can prepare. So please try to come during my office hours. If you need to come at another time, just schedule it with me, like email me. Don't come between 1 and 2 p.m. on a whim because I'm going to be unprepared and frantic. So that happened today. And I was I don't want to be, I want to be as helpful as possible. So just, if you want to come, please email me in advance. I know that a lot of the time you probably don't know you need help until 2 o'clock because you wait till then to finish the homework. But yeah, please just try to come during my office hours, and if not, just let me know in advance.
That was going to be my question. I was going to be like, are you going to be disappointed if we come with our homework barely completed?
I mean, if you come to my office hours, I won't be any more disappointed in you than I've been in previous students, because I've had a student who showed up every day to my office before class having not even touched the homework in CP 100, so it can't get worse than that. So I might be upset, but I won't be as upset as I was with that student. Okay, so that's those two things. As far as the homework, did anybody have any questions? Yes.
I tried setting it up how it was in the diagram, number 1. Yeah.
This one?
And my switches wouldn't alternate, so I have to just connect the node to switch 2. But I was wondering if you could show how to make it work.
Your switches weren't they weren't flipping?
They were closed at the same time and open at the same time.
Did you potentially not flip the polarity?
I did that.
You did do that? I'm thinking you didn't. Something's telling me that you may not have. I mean, if I do it, I'm going to do what I did, and it's going to work. So I'd have to kind of see what you did, but there's no way for me to do that. I mean, I can pull it up in Spice, but I don't think that's going to be very beneficial. Do you have the file, like, on hand?
No, I just, in my homework, I just connected the wire.
Can I see your homework, if you don't mind me seeing it, or everybody seeing it? Should I show everybody? I'm going to make an example out of you.
Okay.
Yeah, we can see what went wrong. Maybe I can just look at it and determine.
So yeah, the only thing I changed was connecting that wire.
Somebody stop me at 2:40 on the homework in case I go over, because I really have a lot to cover today. Well, something's telling me that if I put this in Spice, it's gonna work. So I don't know why it wouldn't have worked for you, but I can throw it in there.
Yeah, just my VS was matching the.
By any chance, did you? Okay, so I have this down here, obviously, but I made this pulse statement part of this source, and I dragged it down there, and I just put this here as a comment for your information. Did you by chance write this out and not link it to this source?
No, I did the same thing.
You did the same thing? Okay. Well, I don't want to take too much class time like on this because it could potentially take a long time. Maybe we can talk about it after. Do you have time after?
Yeah, no problem.
All right, then we'll just do that so that we don't waste any time. Yeah. All right, did anybody else have any questions? About the homework? Yes.
So, can I come as well? Because I have the same problem. So, after class or?
Yeah, after class. So I do tutoring in TBE from 4 to 6.
Okay.
So if you just want to come with me,
Okay.
we can go over there and look at it.
Okay.
Anything else on this homework? Everything was good? Yeah. Yeah, I'll do this one real quick. Some people came to my office about this one too, so let me just do it real quick. I need to introduce something that I haven't talked about yet that I probably should have by now. So let me just draw it out. All right. Nice. Okay, so, oh crap, I need to know the values. 500 pico. 30K. Okay, so did anybody have a problem finding tau? Somebody asked me about tau on this one. Everyone knows pico is 10 to the minus 12? Alright, so I think your tau should have been 15 microseconds if you did it right. Does that sound right to everybody?
Yeah.
Okay. Alright, so let's go back to the camera. I started at 3.3 volts and I pulsed down to 0. And then I think I gave you the initial condition that the capacitors, yep, the output is 0. So this is initially 0. Right? And this is initially 3.3. Oh, sorry. I just want to get the time. So it's 15 micro. Okay. All right. So this is initially 0. This is initially 3.3. That's clear to everybody? That means my capacitor is initially charged or discharged. Okay, yeah. So my capacitor is initially charged. Right? There's a voltage across it. So then at t equals 15 microseconds, right? This source pulses from 3.3 down to 0. Okay? So this voltage goes from what was 3.3 down to 0. Okay? Well, we know that the capacitor voltage cannot change instantaneously. So when this voltage drops by 3.3 volts, the other plate of the capacitor, that voltage also needs to drop by 3.3 volts in order to maintain the voltage across the capacitor. Okay? So if my input looks like this, it's sitting at 3.3 and it drops down to 0. My capacitor voltage, this, or at least this plate, is sitting at 0. So this is 3.3, this is 0. And then let's draw like a separator between these. This is my V in, I guess. My V out is down here, my V in is up here. And this is 0. When this drops, this has to drop with it so that the capacitor voltage doesn't change, okay? So this drops down to negative 3.3 to maintain that 3.3 volts across the capacitor. And then, once we're sitting here with this at negative 3.3 volts, after this switching has occurred, now we're just sitting in a state where we have the capacitor discharging back down to 0 volts across it. And if 0 volts are going to be across it, that means that this has to go to a final value of 0 because the other side of the capacitor is at 0. Okay? Does that make sense?
So is this because the current's flowing in the opposite direction?
Yeah, exactly. So initially, like if we were charging this capacitor, right, when this goes up to 3.3, this goes up to 3.3 with it, and so we get a current flowing in the circuit like that, right, which charges the capacitor. This time, when this goes back down to 0 and this goes to negative 3.3, ground is still right here, so it pushes a current in the opposite direction, right? Any other questions about that? All right, so I want to talk about this equation. I haven't talked about this yet, but it's nothing crazy. It's called the Fife equation. Fife. And all it is this is the equation where the charging and discharging equations come from. Okay? We haven't looked at this yet, but you've already been using it. You just don't know that. Bless you. I was going to derive it, but I think derivations take too long, and I don't want to take too long on this. So if anyone wants to see it derived, I can make a video. I'll ask after this if anyone wants to see it derived. But all it is it's telling me that the voltage across my capacitor at any time is equal to the final voltage of the capacitor plus the initial minus the final times e to the minus t over tau. Okay? It's called Fife because it's final, initial, final, e. I didn't come up with that. It's not me, so don't roast me if you don't like it. I learned it from Baker. He might have come up with it. You can roast him. But it's not me. But what I want to show you is that this is where the charging and discharging equations come from. So if you ever run into a point where the charging or the discharging equations that I gave you don't work, you have to go back to this equation, because the reason why they're not working is because this is for some general case. Okay? So for the charging and discharging equations I gave you, we assume that if we're charging from 0 to some final voltage, right? And if we're discharging from some voltage to 0. But that's not always the case, right? In this case, I'm charging from negative 3.3 to 0, right? So if you were to put the final value of 0 here, like you've been doing, you're going to get 0 for everything, and it's not going to work, okay? So let me just explain what I mean. So for charging, we assumed that we were charging up to some final voltage, VF, so I would just say VF is equal to VF. And we also assumed that we were starting from 0, so my VI would be 0, right? So if I were to write this equation given these parameters, I would say VC of t is VF basically minus VF e to the minus t over tau, right? Because my V initial is 0. So I can factor out a VF, and I get 1 minus e to the minus t over tau. And that's where the charging equation came from. You see that? Okay. But if I'm not starting at 0, this doesn't work. So if you were going to use that equation for this problem, you have to go back to the general case, where in this case my final voltage is actually 0 and my initial voltage is negative 3.3. Does that make sense? You guys see that? It's initially negative 3.3, and VF is going to be 0 in that case. So I wanted to give this to you because it's probably best that I should have probably given it to you sooner. I honestly just forgot. So using this equation will work all the time. The other equations that I gave you are not general case. So this is probably the best thing to memorize, because under any circumstances, if you know the final and the initial values of the capacitor voltage, this will work. Okay. So, and then just to be complete, let me show you that this is where the discharging equation also comes from. And you realize then that what I'm saying is this works for charging or discharging, because as long as you know the initial and final voltages, this is going to work. There's not like a Fife charging equation and a Fife discharging equation. It's just this equation, and if you know the values, it will work out to be either charging or discharging. So in the case where we're discharging, our final voltage we assume to be 0. We're going to discharge to 0, and our initial voltage is just VI basically. So if I plug 0 in for both of these VFs, right, I'm just going to get VI times e to the minus t over tau, and that's the discharging equation. Okay, so that's where the equations come from, but I think it would benefit everybody to memorize this equation because you can use it all the time. Okay? And actually, I think you're going to need it on today's quiz, so hint, you're going to need it on today's quiz. So write it down somewhere now. I'll give you guys 30 seconds. And then just try and, if you don't memorize it, honestly, I'll let you use wherever you write it down today on the quiz, because it's my fault for not teaching it to you sooner. You know what? I could just put it on the whiteboard when you guys are doing the quiz. Let's just do that. There. Can everybody see that?
Yeah.
If you can't see it, then
You can just write it on a piece of paper.
I can just write it on the paper before the quiz. Yeah. All right. So we got that out of the way. Any questions about this? Yeah.
What's the side on top of the E power negative T over
Tau. Tau is the R times C. Yeah, tau RC. All right. Any other questions? Okay, now I'm going to get into the final little segment on RC circuits. They're a little bit more complicated, but I think I just, the other day, in trying to figure out what was the best way to teach this, determined a new method of solving these that's going to make everything a lot easier for everybody. Like, it's not brand new, it's using KVL, but I've never seen it done this way, so
Can we call it the James?
sure. I'll take that.
Actually, no, spicy cake.
No. No, please no. Okay. Well, what I want to start with this problem, this particular problem, because I'll show you that instead of having to memorize what's happening with the capacitor, you don't have to memorize anything. You just use KVL and it'll work. And I think it's great. So I'm going to show it to you using this example, and then we'll use an even more. Stop. Stop. Throwing me off my game. It's okay. You can throw me off. All right. So I'm going to title this Using KVL to Solve RC Circuits. Okay, so let's go back to that example. Okay. This is 0, this is 3.3. We'll call this is V out and this is V in. Alright, so in this previous example, I just basically told, we're just like looking at a bunch of nodes and trying to kind of memorize what's going to happen, maybe not getting a full understanding of what's happening. So I've described what's happening. The capacitor voltage can't change instantaneously, and you're still going to have to remember that. But let's just say we know that after the capacitor, after this side of the capacitor, basically, after Vin goes down to 0, we already know that there's 3.3 volts still across. Oh, am I going the wrong way? It's plus to minus the other way. There's 3.3 volts still across the capacitor, right? We know at that instant, when the pulse goes to 0, the capacitor stays charged to that same voltage because we can't change it instantaneously, okay? So let's use KVL. I'm going to change colors. I'm going to draw a current flowing in this circuit, I. And so if I were going to do KVL here, and I start at this this node right here, I'm going to go across the capacitor. And I know that across the capacitor, I drop by 3.3 volts, right? So I'm going to write minus 3.3 volts. Okay? And then when I go across the 30K, I get minus I times 30K equals 0. Right? Everybody good with that? You have a question?
Yes. How do you get negative I into 30?
I mean, this is just KVL. If you don't,
Oh,
like, it's just when we do KVL, like when we do mesh analysis, right? You're dropping by I times R, like it's Ohm's law. The basic voltage drop across this resistor is whatever this current is times this resistance, right?
I was thinking it to be positive.
Oh, well, I always do it to be negative because I'm dropping. You can do it however you see fit, but this is how I always do it. So I see dropping voltage, so I put a negative, right? Okay.
That makes sense.
So now I'm going to solve for I. I'm going to say negative 3.3 volts equals I times 30K. I'm going to divide both sides by 30K. And that's going to give me I equals negative something. 9.09 what? Milliamps? Negative 9.09 milliamps? You're not confident enough for me to take that.
My calculator was bad.
I didn't get that. Yeah, I got 0.11 and something's not right over there. Did you do 30K divided by 3.3? That might be the problem. So negative 0.11 milliamps. Is that what we all got? Like this. Okay? Everybody see that? So that's my I. So that means I guessed wrong, right? The current wasn't flowing this way, it's flowing the other way. So let me redraw the circuit and I'll draw the current flowing the other way. And realize I put a short here because it's 0 volts on both sides, right, of the battery, so it may as well not be there, but I could draw it. It has 0 volts across it, so there's no point in really drawing it. Okay? So instead of the current flowing the way that I thought it was flowing, it's actually flowing this way. Right? And that's 0.11 milliamps. Right? Okay, if I have 0.11 milliamps flowing in that direction, and this is 30K, I know my drop is like this. And if I multiply 0.11 milli by 30K, I'm going to get 3.3 volts dropped across that resistor, right? Which means this node, since this is 0, is going to be negative 3.3 volts. You see that? And that's exactly what we got over here. We got that at that moment, that voltage is negative 3.3. Okay? So the thing with this KVL method that I realized is you can use it on the edges when something's pulsing up and when something's pulsing down to determine where do these values go. And then after that, the charging and discharging equations take over, basically. And at this point, to determine what the final value is here, you just have to note this node is still connected to ground through a resistor. So eventually it's going to go to 0 volts. And so that's how we can say, oh, okay, it was sitting at 0, it dropped to negative 3.3, and then it's going to go back up to 0. Does that make sense? Okay. So now I want to show a little bit more complicated of an RC circuit, and we're going to analyze it from the old perspective, just looking at it and kind of eyeballing what's going on, and then we'll solve it using this KVL method because I think that that's the best way to do it because some weird behavior starts happening. So I want to take an example from the homework because there's a couple of tough ones on there and it's due Wednesday. So I'm going to take this first problem here, but I'll change some values. So let me just stay on the same page. Let me draw the circuit. All right, so it goes 0 to 5 at 5 microseconds, and it stays high for 10 microseconds. All right, this is V in, this is Vx, this is V out. 1K, 1K, 1 micro. Ugh. Hold on, sorry guys. You know what? Whatever. I'm just going to change this to milliseconds, and it'll be fine. Alright, so what I've got here is a circuit where I've got a resistor, a capacitor, another resistor, okay? And basically, I'm going to see that my source is going to go from 0 to 5 at 5 milliseconds. So let's just start by looking at that part. That's going to be my charging part. My capacitor is initially discharged, which means it has 0 voltage across it. Okay? This is 0, that means this is 0, that means this is 0. So everything's 0, okay? Now at 5 milliseconds, this is going to jump up to 5 volts, okay? We have to keep 0 volts across the capacitor, right? So that means something's going to happen in this circuit that's going to keep 0 volts across this capacitor. But if we look at it, do you guys remember when I said that over a fast edge or in AC, a capacitor acts like a short? Okay? So if we had a short here and that capacitor was just a wire, what is this circuit? It's just a voltage divider. So what would V out be in this case? That's exactly right. It's 2.5 volts. And Vx and V out are connected if this is a short, right? So Vx would also be 2.5 volts. Okay? And then after that brief moment, right? After that brief moment where this occurs and the capacitor acts like a short, we re-evaluate the circuit. And what basically happens is now we have 5 volts minus 2.5 volts over 1K, right? We have a current flowing this way. And then we have 2.5 volts minus 0 over 1K, so we have a current flowing this way. And now the capacitor charges because of this current. Okay? And again, like I said, we're going to have to kind of look at these circuits to see what these values are going to eventually go to after the switching. What is V out eventually going to go to? It's going to go to 0. Because it's connected to ground through a resistor. What is Vx eventually going to go to? When there's no current flowing through this resistor and this is stuck at 5, what's Vx going to be? It's going to be 5. It's going to be 5 because no current will be flowing through this resistor eventually once the capacitor is fully charged and my input's stuck at 5. So with no drop across this resistor, this will eventually go to 5, right? So what we would see if we plotted this in SPICE is we would see these two nodes that were initially at 0, they would both jump up to 2.5 at the same time. And then Vx is going to charge to 5 volts. And V out is going to discharge down to 0 volts. So that then at the end, I have 5 volts across my capacitor. So that's how my capacitor is charging in this case. This probably seems wildly complicated, and it is wildly complicated. But with the KVL method, it becomes far less complicated because, and I'll go through it, but it's just, basically you don't really need to think about it as KVL. You need to think about it, I mean you can, but when this goes to 5 volts, right, when this input goes to 5 volts, I could write my KVL as 5 volts minus I times 1K. Then I get to the capacitor, and I know that initially there's no voltage across it, right? It's initially discharged, so I don't have to look at it in KVL. The voltage across it is 0. So I could write a plus 0 or a minus 0, but that's not going to change anything. And then again, I have another minus I times 1K equals 0. So if I solve this, I basically get 5 volts equals I times 2K. I divide by 2K, and I get I equals 2.5 milliamps. Okay, so if I is 2.5 milliamps, right, and I know I have 5 volts on my input, I'm going to drop 2.5 volts across this resistor, right? So that gives me 2.5 here. And I know I have 2.5 volt drop across this resistor, and this is 0, so that's going to give me 2.5 here, right? So now you see the KVL method works. And now on the discharging side, it gets a little crazy. Let me put this in SPICE so that we can talk about it, because I'm running out of room, and I think it's easier to just talk about these circuits on SPICE. So homework, what was this? Homework what? 14? Alright, so I put 1K, 1K, what did I say, 1 micro? Oh, interestingly enough, so tau in this case is going to be R times C still, but since my resistors are in series, I have to add them, okay? If my resistors were in parallel, I would take the parallel, and that would be my R for my RC, okay? So in this case, I have series resistors. My tau is going to be 2K times 1 microfarad. Everybody fine with that?
Don't forget to do your pulse timing and transient.
Yeah, I'm going to change all that. What's that?
How would you have RC circuit and have parallel resistors? Would it just be like parallel in one of the resistor places? Okay.
Yeah, so if I like threw another resistor out here,
Right.
I would have 1K in series with whatever that parallel is, and that would be my... Or there's a case where...
Because I was thinking if you had the capacitor between the two resistors and they were in parallel, isn't that just the same as having the resistor connected? Didn't we already have that in the last one, basically?
Yeah, but I have to do the switches.
Okay.
Always have to do the switches. I don't want to
You know what? Let's just sim it. I might be wrong. Because it might be the case that I know that the capacitor is going to discharge through these two paths, and my intuition tells me that since it has two paths to discharge, it would discharge twice as fast, which makes me think that the R should be 500. It should be the parallel of these two. So let's just sim it and see what happens. What was I going to change? Oh, these are all fine. I have to change this stuff. So instead of 5 micro, I'll do 5 milli. And then I'll do 20 milli for how long it stays on. And then I'll sim for 25 milli. Alright, so let's run it. Actually, you know what? I first want to just sim for the first cycle here. Yeah, this is fine. So my input goes up to 5. My VX goes up to 2.5. Hold on. This is so annoying. Okay. See how it goes up to 2.5 and then charges up to 5? And then V out goes up to 2.5 and then charges down to 0. So then at the end, in this steady state over here, Vx is 5, V out is 0, so my capacitor is charged to 5 volts. It has 5 volts on one side and 0 volts on the other side, right? But the tricky part is what happens on this edge. So if you want to think of that as a short and then this becomes a voltage divider, that will always work, right? So if R2 was 1K and let's say R1 was 3K, right? Then it would be a voltage divider where this is 1K and this is 3K. But again, this capacitor is going to act like a short, so this Vx is going to go to the same as this V out. You just have to calculate what that voltage divider is going to be. Okay? Yes?
So you're just looking for what's the initial, what's the final, so 2 KVL, right? Too short.
Yeah, so basically, well, what I'm looking for with KVL is all I'm looking at is this rising edge. And I want to know what are these values going to start at. And then the final value is up to you to determine, basically. We're going to have to determine Vx1 is going to go to 5 because it's connected to a 5-volt source. V out is going to go to 0 because it's connected to ground, right? So that's kind of going to be the tricky part, is looking at these circuits and realizing, okay, this is eventually going to go to 5 volts. This is eventually going to go to 0 volts. And all it really is noting, like, what is that voltage going to be when there's no current flowing? That's all it is. If there's no current flowing through this resistor, this is 0. If there's no current flowing through this resistor, this is whatever V in is at that time, right? So when we discharge, right, this is going to go down to 0. So then eventually Vx is going to have to go down to 0 with it, right? You had a question?
Yeah, I was just going to say, once it starts discharging, the Vx then drops back down to 2.5 before descending to 0? Or would it go down past 0 and then work its way back up?
Hold on, I'm sorry. Can you repeat the question?
So I was going to say, when it starts to discharge,
So you want me to plot the discharging?
yeah, essentially.
All right, so let's plot for like 50 milliseconds. Or let's do 60. Because this is some interesting behavior. So what was your question?
I'm basically asking if that's exactly what was going to happen. VX would drop down to 2.5 before descending to 0, and then V out would drop below to negative 2.5 before coming back up to 0.
So you already knew that was going to happen?
Yeah.
I didn't even know that was going to happen.
It would work backwards, essentially.
Well, it's the same way with like the last homework where it would drop down. If one drops down, the other also has to drop down.
Right, but how would you know that this is going to drop to 2.5 and this is going to drop to negative 2? What if this dropped to 0 and this dropped to negative 5? Or what if this stayed at 5 and this dropped to 0?
No, because it reacts the same way when you charge it. It turns into a short.
It does, but if this is 2.5 and this is negative 2.5, then that's not a short. So that's why I got confused. That's what confused me. That's what led me to look into a new method to solve these. Because if I think this is a short, I would assume the voltage on both sides is equal. But in fact, it's 5 volts apart. I mean, if it works out for you, however you understand it, I mean, more power to you. But I personally didn't like thinking of it as a short because now it's not a short. It's not really acting like a short anymore. What is happening is if this goes down by 2.5, this also has to go down by 2.5, right? But what was bothering me was how do I know this goes down by 2.5? How do I know that? Why doesn't it go down by 3? Why doesn't it go down by 2? Like because if I change these ratios of resistors, it does change how much it goes down. So like for example, let me change this to 2K and this to, I guess I'll change this to 2K also. I think it's going to cause some problem. Oh, that's because they're the same. Sorry. See, now it only goes down, it doesn't go down to 2.5, it goes down to some other value. And so basically, if the values weren't equal, obviously now we know if my two resistors are equal in value, it's going to go down by half. But if they're not equal in value, then what the heck happens, right? That's why I want to introduce the KVL method, because no matter what the resistors are, it works. So you're right. You were right. Exactly what happened. But I don't know if that will work out every time. I know that the KVL method will work out every time. Yes?
Would the drop be the same as the rise when you're charging it? Would it always be equivalent? So if you drop, so in this case, it rises by 2.5, and in the other case, it drops by 2.5. And then in this case, if we calculate that, that's whatever number that is when it then drops by that same amount.
That is true. But the reason why that's true is because the same current is flowing.
Correct.
But I don't know. You're right. Everybody's right. Everything you guys are saying is correct. I wanted to provide a general method to use every time. So like this method will work for all the homework problems. This one and both of these, the KVL method will work. Even these problems where the capacitor is now somewhere else. Okay, and I want to correct myself here. I'm fairly certain that you have to take these in parallel. Because when this goes to 0, those resistors are in parallel. And you have two paths for the capacitor to discharge. Okay? In these cases, you only have one path. Right? The capacitor can't discharge through anything this way. It has to discharge through these resistors. Okay? So you would take these in series, and your R would be 4K, and your C would be 5 micro. And here, your R would be 10K, and your C would be 10 nano. In this case, your R is going to be 250. It's going to be 500 in parallel with 500. Because you have two paths for charges to take. Okay, let me show you what's happening at the electronics level, like the electron level, because that might not make any sense. So if I'm sitting here in that circuit that we just had, and I have basically a source, a resistor, a cap, a resistor, right? When this source goes down to 0, my equivalent circuit here would be something that looks like this. This could basically be ground. I've got a resistor, a capacitor, and I've got a resistor. Okay? Does everybody see that if this is 0 volts, those two circuits are equivalent? Does anybody not see that these two circuits are equivalent? Okay. So if I have this capacitor charged, basically what's happened, so let's say I have charged this capacitor and I have a voltage of some voltage, let's say VC across it. What has happened is I have attracted some extra electrons onto this plate, right? These electrons push other electrons off of the other plate, which makes this side slightly positively charged, right? So when this capacitor is charged, what we have is we have some excess electrons on this side, and we have some, it's not necessarily excess positive charges on the other side. What it is it's the lack of negative charges, which look like positive charges.
But it could be positive ions.
It could be. But I think in most cases,
You're just pushing it away.
it's pushing away other electrons. It's repelling the electrons that were here this way. Okay? So, when I discharge the capacitor, what's happening is basically these electrons, these excess electrons are leaving the plate, right? So those excess electrons are going to come down through this resistor back to ground, or wherever they came from. And electrons that left are going to return to this other plate. So let's say these 4 electrons leave and 4 more electrons come. Then I would end up back in the neutral state where the capacitor is not charged anymore. It no longer has an electric field across it. But because we get not only one path for electrons to flow off of the capacitor, we also have a path for electrons to flow back onto the other plate. These resistors act in parallel because we have 2 paths for the electrons to flow. Where in the case that we were just looking at in the homework, we don't have any resistance down here. So everything is going to happen in series through this one plate of the capacitor. So does that make sense?
It seems kind of counterintuitive in that, like, there's no resistance, so we can't have a current because there's no resistance. But again, that seems counterintuitive.
I think it's more or less because it's ground. If I threw 2 more resistors down here, you would take those 2K in series in parallel with these 2K in series.
Well, it makes sense because after you put the last one, I understood it exactly because the capacitor, they don't share that node. There's a capacitor between them technically, but then they do both share ground, so
they're technically in parallel.
They're technically in parallel if you don't consider the capacitor. If you consider the capacitor as like a power source or something else, and in this case, it seems like it's kind of acting as one because it's the only thing that's really holding charge that has any kind of voltage within the system.
Right,
So
and
once
what
you did that, I was kind of like, oh, okay, I get now why you do it in parallel.
Yeah, because here they're in parallel. I mean, they're not in series. But if I say they're in parallel, I have to say they're sharing 2 nodes. And if I say they're sharing 2 nodes, they're not. They're not. They're only sharing ground technically. But yeah, so this is kind of touchy. Like we like to think about all these things in terms that we understand, right? But technically, in steady state, these aren't in series or in parallel. I mean, they're in series. They are in series because the capacitor is just another component. But in DC, we treat a capacitor like an open. So what we would really be looking at is a resistor floating and another resistor floating. So all of these things are kind of touchy, right? They're not in series, they're not in parallel, but we treat them in parallel because there's 2 paths for the reason why, if we have a current here and it flows into these 2 resistors, the reason we say they're in parallel is because that current can now split into 2 different paths. It's kind of that same principle. The charges have 2 paths that they can take, so they're in parallel. Where over here, and I get what you're saying too, because you're like, well, what the heck? Wouldn't this just be like a 0 ohm resistor? Well, yeah, it would, but it's ground, so technically no current flows on ground.
Right.
I mean, it does, but we say that we basically imagine a current flowing out of this battery and then like returning to ground and kind of stopping, even though it is circuitable.
I understand why the resistors are in series, but it's weird that we don't consider it as having 2 places to discharge to.
Right. Right. Well, because I guess in this case, what would happen is you would build up charge on this plate, and then that charge would just return back from where it came from. Where in the other case, you're not only building up charge on this plate, you're also repelling charges from the other plate. Like and that's why both of the plates are moving in voltage, right? They're both simultaneously doing different things. Let me go back to the initial example. Is this it? Yeah. So like both of the nodes are moving around, so charges are moving on both plates. Where if I were to plot, the other case where, let me just move this. Let's just look at it.
Does it ever annoy you that the capacitors are different sizes?
Always.
Different voltages?
It annoys me every time I use Spice. I don't know why they would do that. Because the inductors are the same size, the voltage sources are the same size. Why did the capacitor have to be smaller? I don't know. So let's look at this one. This node never moves, right? The bottom plate of the capacitor is always ground. I can't even plot it because it's like, this is ground. What are you trying to plot? 0. Don't you know that? It's like, it's taunting me. But this node is moving. And so in this case, we see what happens again. The capacitor instantly acts like a short, right? So V out stays at 0. Vx goes to 2.5 because, again, this is just a voltage divider. And then eventually, they both go up to 5 volts, right? Because what is V out connected to? Ultimately, it's connected through 2 series resistors to 5 volts. So when no current's flowing, they're both going to be sitting at 5 volts, right? And then when it discharges, see, this is where my confusion comes in. Why does when this goes to 0 and this is sitting at 0, what makes this jump to 2.5? That's why I personally like the KVL method, because I wouldn't just know that off the top of my head. And I definitely wouldn't know if I changed these, But what you said was true, right? Whatever it goes up by, it goes down by the same amount. But I don't know, that's just, it's not mathematical enough for me.
But it looks like this. It goes by the inverse amount of what it went up by.
Yeah, if it went up by 2.5, it goes down by 2.5.
Yeah, but if you change them to have different ratios.
If it goes up by 2, you think it'll go down by 3?
Yeah.
I think it goes down by the same amount.
I think it goes down by the same amount.
See the red? It goes up by 1.25, it goes down by 1.25.
Oh yeah, my bad. I was interpreting that.
But as an instructor, do you think I could just say, if it goes up by this much, it goes down by the same amount, and you guys would feel satisfied? I don't think so.
No, I'm not saying that. I'm just trying to.
You're right.
I'm right. I don't like it either. I'm just trying to work it right.
I mean, you're right. So if it works for you, it works for you. But now I'll prove it. Let me prove it. Let's do a KVL. This one or the previous one?
Would you actually mind putting the resistors back in parallel with the capacitor in the middle, and then changing the resistances to be the 1K and 3K again?
And do the same thing.
It goes down by.
It still goes down by the same amount. So it went up to 3 point something, it goes down by 3 point something, right? So same thing.
I don't know. I just think of it as the displacement. Right?
Yeah, I mean, you're right. Whatever it goes up by, it goes down by. So if that works, that works.
Well, I'm thinking now if we just take to like the component portion on this side, this one will go up by this many electrons, and this one will go down by that many electrons. So then when you inverse it, you flip the whole damn thing, then this one will somewhat immediately go up by that many electrons, and this one will go immediately down by that many electrons until they balance out to 0.
Sure.
I don't know, man. I'm just.
Hey, just stick with it. You're right. You're right.
The thing that they were saying, like, oh yeah, freaking electrical engineering makes no damn sense some of the time.
Well, it does make sense because KVL makes sense. KVL always works.
Yeah, if you simplify the circuit, if you simplify anything, it makes sense.
I didn't simplify the circuit. I just used the exact circuit that we had. Where is it? Hold on. I didn't simplify it. This is the same circuit. I just wrote a KVL loop for that circuit. Yeah, I didn't simplify it. KVL is always true. At any point in this circuit, KVL will work. It will work. So even somewhere down the line while it's charging, 1 microsecond later, KVL will hold true. But that wouldn't be very fun, right? It makes more sense to use the equation for the next however many times constants than it does to do KVL an infinite number of times, right? But yeah, I mean, whatever works for you guys, whatever can help you understand it, I'm fine with. I'm not going to ask you to specifically use this method. I just wanted to provide a method that you can use systematically every time you see a circuit. Because this even works for the original RC circuits, like the first couple that we saw on the first homework. When was that? This one? Nope, not that one. The one that was due today, maybe? Yeah. If you do the KVL method on these, it works. I mean, you don't need it really on these because what's happening is pretty intuitive. Did somebody have a question? I thought I saw a hand. Okay, so let's go and do another, like a quick KVL with one of these and then show that in Spice it works out. Because that's basically what you're doing on the homework. Where am I? I guess I should use a new sheet. This is kind of crappy. Alright, so let's say we've got, let's just throw something together. Does anybody have a preference? Does it, out of which of like the homework problems seems more daunting? Is it these type or the top one? Both? Well, I don't have time to do both. This one? Alright, the one that's parallel? Alright, let's do that one. Well, I just did it, so let's just pick some new values. Let's say 2K. Let's take a 2 nanofarad and then another 2K. Or let's do a 6K. Alright. Let's say it goes 0 to 10 volts. So initially this is going to be 0, this is going to be 0, this is going to be 0, this is going to be 0. Alright, so when I first pulse up to 10, right, what I have is something that looks like this. Call that I. And I have 2K, 2K, right? So I don't know what my, I don't care what my capacitor value is. I just know that its voltage is 0. So for the KVL, I don't really have to consider that voltage. I can add it or subtract it. It's just 0. Okay? So if I'm going to write my KVL for that loop, it's going to be 10 volts minus I times 2K minus I times 2K. Huh? Oh, it's 6. Thanks. 6K equals 0. Sorry. So that's going to be 10 volts equals I times 8K, right? And I divide by 8K. I am assuming that's 1.25 milliamps. Is that right? Yeah? Okay. So I can either go, 10 minus 2K times 1.25, or I can just do the voltage divider. It's going to be 10 times basically 6 over 8. 7.5 volts. Which makes sense, because if I say that this is 1.25 milliamps, that means I'm going to drop 2.5 volts right here, right? If I drop 2.5, that gives me 7.5, and this side is also going to be 7.5. Okay, so that what that means in my plot is my, Vx, I guess I'll call this, like I have, and V out. They're both going to start at 0. They're going to jump up to 7.5. And then one of them, Vx, is going to continue on to 10, and the other one is going to drop down to 0 until, in steady state, my capacitor voltage is equal to my source voltage, right? It's going to store all that charge that was dumped out of the source. Okay? So now the question is, sometime later, let's just dot this. We've got Vx sitting up here, and we've got Vout sitting down here. And the question is, what's going to happen when this drops back down to 0, right? What's going to happen? Well, if I were to redraw the circuit, I've basically got 0, I've got a 2K, I've got a charged capacitor now, a charged capacitor which has 10 volts across it. Another resistor and ground. Okay? So now, what I have happen is I'm going to do another KVL. So this is my first KVL, and this is for charging. And then this is my second KVL, and this is for discharging. Alright? And so, what I'm going to do is I am going to, I'll draw my current I. Let me change colors. I'm getting tired of this blue. So I'm going to go minus I times 2K. I'm dropping 10 volts. And then minus I times 6K is going to equal 0. That's going to give me minus 10 volts is equal to plus I times 8K. And then I'm going to get that I is equal to negative 1.25 milliamps. Right? So there's the proof that the current's going to be equal but opposite. So instead of what we thought, it's actually going to flow the other direction. Okay? So if I have negative 1.25 milliamps across this 6K, that means that this should drop to negative 7.5, right? And this side should go back to positive 7.5. So if I were going to plot that, this one's going to drop down to positive 7.5, and this one's going to drop down to, I guess it would be down here somewhere, negative 7.5, and then they're both going to tend back towards 0, right? Because I have 0 on both sides. So in steady state, they're both going to reach 0.
I think the left node is supposed to be 2.5 instead of 7.5.
Yeah, when it drops 7.5, not drop to 7.5.
Oh, is that what I... Yeah. Because it's negative 1.25. Yeah. It's negative 1.25 times 2K, which gives me a drop of 2.5. So yeah, this is going to go down to 2.5 and then discharge. Sorry. Alright, let's throw it in Spice real quick and make sure that that's exactly what happens. That should be exactly what happens. So what did I have? 2K, 6K, 2 nanofarads. I'm going to have to change all this. Let me calculate some stuff. 6 times 2 over 8.5, 2, 3 microseconds.
That's supposed to be 10.
I just threw some values in there so we could see it.
No, but it's supposed to be 10 volts.
Oh yeah, it is supposed to be 10.
Yeah.
I thought you meant the time.
Yeah.
Alright. Oh, hold on. What did I do? It's not having enough time to discharge. I think this is supposed to be much longer. So what would my time constant be here? Maybe it is series. Maybe I did that wrong. So 8,000 times 2 times 10 to the minus 9. If it's series, that means that my time constant should be 16 microseconds. So that means we need it at least 80 microseconds to see it fully discharge. Alright, in that case, let's see what happens if I change this to staying on for like 100 microseconds. And then I sim for like 300. Alright, so let's take a look at what my time constant actually is. We're going to find out. Okay, so this is, it's discharging from 7.5 to 0, so it's going to discharge to, let's see, sorry, it should be 2.775 at, what is this time? 5 microseconds, so at 21 microseconds. Okay, yeah, so it is series. You know what? I'm not going to give you guys a quiz today because this has just been all over the place. I'm assuming in that case that all of them will be series. But my original assumption...
Parallel.
What?
I said it made sense for them to be in
It,
parallel. It's ridiculous.
it did make sense for them to be in parallel to me too. That's why I thought they were in parallel. Okay, so if they're in series...
So is it because it kind of short circuit and basically high centricity is going straight through the capacitor, which makes it series?
Well, I mean, technically, like I said, they are in series. They're actually not in parallel. I mean, let me go back to the camera.
How did you pull up that little window that has the cursor that shows you what your values are?
Oh, yeah, if you just click on the name of the trace,
Okay.
you can, what did I click on? V out? Yeah, so you see how it's like got a little dotted box around it?
Okay.
And then if you right click, you can get 2 cursors if you want. And then you can like measure the difference between voltage using them and all this other stuff. But yeah.
Cool.
Yeah, so let's look into this a little bit more. Okay, so when the capacitor discharges, like in this case, let's go back to the camera. When I'm looking at this right here, right? They're in series. They're in series. If I were to draw this, I could draw it like this. So they share one node. They share ground. They don't share 2 nodes. So in that case, for your homework, just so you do everything right, my assumption is they're all series. Because in every case, when this goes to 0, they're going to be in series. And in this case, when this goes to 0, they're still going to be in series, and same thing here. So treat them all as series. I don't know if they ever take the parallel R. For some reason, I thought that was the case, but clearly that's not the case.
So then basically, it doesn't matter if the capacitor is between them, front or back, they're still considered in series.
Yeah, I mean, I would assume so based on what we've seen in SPICE. And it does make sense that they're in series, but for a second it made sense that they were in parallel, but clearly they're not in parallel, so treat them in series for this entire homework. Do you have a question?
Well, it's more like, did you draw later or like earlier in the lecture when basically how you treat it is like 2 floating resistors? So basically the only way that they're connected is by ground itself. Yeah.
Yeah, so they're literally...
They're in series technically because of the capacitor. You just take out the
Yeah, I took the capacitor out because in DC, you treat the capacitor like an open because no current can flow through it. I took it out because this was what I was saying, like DC, the cap behaves like an open, right? And it does. So like when you're sitting in DC, if you look at any of these circuits during like steady state, like right here, the capacitor behaves like an open once it's fully charged because this side is at 5, so no current flows through this resistor, so this is at 5. So it would behave exactly the same as if I just took it out, right? I would have 5 here, I'd have 5 there, I'd have 0 here, I'd have 0 there. So that's DC. All the interesting stuff happens during the switching, during the charging and during the discharging. But yeah, I guess it does make sense now that they would be in series. But for a second, I thought they'd be in parallel, but clearly that's not correct. So for this homework, treat them all in series. I can't think of a case where they would be in parallel, actually. Because this is like all of the possible RC circuits that you could see. And in every one of these cases, I see these resistors being connected in series.
Well, if you had that, like you talked about earlier, like another resistor sticking off the side of those would be
Oh, those would be in parallel. But that's just like, that's still, it's just an equivalent at that point, right? So yeah, I guess in that case, so like if I were to put another resistor here,
Yeah, that would just be equivalent.
that would just be 3K now, right, in series with this 2K. I mean, the thing is, right, when we get into AC stuff, like when you guys take 221, and I'm probably gonna go over it before this class ends. Not today, but the course ends. Yeah, sorry, not today. No. This would be considered a series circuit because remember, series is, the same current flows through the devices, basically. These two resistors are in series right now. They're just, you can't take an equivalent because they're not next to each other. But if you were trying to find like in AC, capacitors, resistors, and inductors, all these components, they have what's called impedance. And impedance is basically like resistance, except for capacitors and inductors, it depends on the frequency that the circuit's running at. So your capacitor, basically, let me just overview this since I'm not giving the quiz anyways.
Why not call it spicy resistance?
Yeah, you could. I guess you could. I'm just gonna go with whatever you guys say from now on. I've had enough. You're right. All right. So resistors, right? I'm just gonna overview. This is just for your interest, because you have everything you need to do the homework now, and I'm not giving the quiz. Resistors, we call it resistance in DC. We call it impedance in AC, and it's written as not impedance, impedance. We write it as Z. Okay. So yeah, you have a question?
So wouldn't it be called an impeder in AC?
No. It's still called a resistor.
Wait, what?
Wait, is there an M symbol in circuits?
Yeah, but that's used for like magnetics. So impedance is Z. It's not going to be shown as R. Okay? But the impedance of a resistor is equal to its resistance. Okay? There's no frequency dependence at all. Okay? But for capacitors, they have an impedance. What is so funny? So dumb. You guys are ridiculous. All right, so this is where complex numbers get involved. The J is used to denote the things in AC circuits that depend on frequency, okay? So a capacitor, obviously the resistor is just R. There's no J involved. Oh, by the way, J is I. That's your root -1. We just don't use I because I is current. So engineers use J for complex numbers, not I. So if you've ever seen that, that's why. Okay? So in this case, my capacitor's impedance is dependent on the frequency that the circuit's running at. You see that? So if this F is 0, right, that's DC. Right? 0 frequency is DC. Nothing's changing. There's no cycle. Okay? If this number is 0, then what is this impedance? It's infinite, right? 1 over 0. So this goes to infinity for DC, right? And infinite impedance is an open. So that's where that comes from. So it's basically, there's a capacitor here, but you could think of it as a resistance with a resistor with a resistance of infinity. No current will flow through it, so it's an open. Okay? Inductors, which we haven't talked about yet, that's the last thing. I'm going to talk about these next time. We're done with RC circuits after today. Yeah, sorry. Today was, I feel bad about the parallel thing. I thought they were in parallel. That's on me.
We're done with RC circuits because we're moving to RLC circuits, right?
We're moving to RL circuits.
Oh.
So they're going to be very similar with some different things going on. So the inductor has an impedance of J omega L, and omega is 2 pi f. I just wrote it as 2 pi f down here. Which means if my F is 0, my impedance is 0, right? So an inductor acts like a short in DC. It has no impedance, right? But as the frequencies get higher and higher and higher, then the inductor acts like an open. Right here, if this gets huge, my F gets huge, and that's like a really high frequency, then my capacitor's impedance goes to 0, and that's why it acts like a short at high frequencies. That's why I said that. Okay.
So what is the purpose of an inductor?
So I have 5 minutes to talk about inductors. Okay, so let's just briefly overview them. So inductors. So the way capacitors work is, right, their voltage can't change instantaneously, right? Inductors have a different property. Their current can't change instantaneously. Okay? So the capacitors and inductors are kind of like inverse components of one another. If I try to change the voltage across the capacitor instantaneously, I can't, and I run into problems. The same thing happens with an inductor, but the current can't stop flowing. Okay? So what an inductor is it's basically just a coiled wire around, and usually coiled around some magnetic material. So Electroboom was talking about this at the beginning. That's right. Usually they call this a ferrite or a ferromagnetic material.
So
And
both capacitors and inductors store charge?
they store energy, yes, they store energy. But they store energies in different ways. Capacitors store energy in the form of electric fields. Inductors store energy in the form of magnetic fields. Okay? So, you may or may not have known this already, but if you take any wire, let's just have a wire, and you send a current through that wire, a magnetic field is induced around that wire. Okay? So if I run a high enough current through a wire, it will act like a magnet. The currents we run through wires on breadboard and stuff aren't enough, but if you run a high enough current, you'll get like a tangible magnet field around the wire. Also, if you take a magnet or any magnetic field and move it past a conductor, it will generate an electric current. Okay? Yeah.
What does the ferrite do again?
The ferrite, it basically increases the inductance. It increases how large of a magnetic field we can generate by sending a current through this wire. Because if you just take a wire and coil it, you can get some impedance or some inductance. But if you put a magnet in between, you get more inductance because now the magnetic field storing the energy is even greater. So if you guys remember, right, I said that the energy stored by a capacitor was 1/2 CV squared, right? The capacitance times the voltage across it squared. The energy stored by an inductor, and I'm going to go over all this again. This is just a brief overview. It's 1/2 the inductance times the current through it squared. So if we can increase our inductance, then we can increase the energy stored. And we can increase our inductance by putting a magnet in here because now we can basically generate larger magnetic fields for smaller currents. Does that make sense? So yeah, inductors have this property where when you basically, so you know capacitors, the voltage was equal to C dV/dt. Okay? Well, for inductors, the voltage, the voltage is equal to L. Oh my gosh, I'm all over the place, guys. I am all over the place. The current through a capacitor is C dV/dt, right? Well, the voltage across an inductor is L di/dt. Okay? And so if I try to change the current, remember how I said, right, if I try to change the voltage across a capacitor instantaneously, what I get is a infinite current, and that can't happen, right? That can't happen. That's why we say the voltage can't change instantaneously. Well, that's the same thing here. If I try to change the current instantaneously, I get an infinite voltage, and that can't happen either. But what can happen is I can change this current really, 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 really fast, because say I have an inductor that's sitting here with a current flowing through it, and I just cut the wire. It will generate an enormous voltage because it wants that current to keep flowing. And so tasers are made using inductors, and by cutting that current, and you get, you have your two prongs of the taser, and you get this enormous voltage here, and that current wants to keep flowing. So what does it do? The charges jump straight through the air, and they will keep flowing. Obviously, there's some limitations to this. You can't just generate infinite voltage, but you can use inductors to generate really, really, really high voltages for a short amount of time, right? So when you look at a taser, it's not a continuous spark. It's a bunch of arcs happening really fast, so it looks continuous, but it's not. It's one pulse, and then some gap of time, and then another pulse, and then another gap of time, but it happens fast enough that it looks like it may be a continuous arc.
Okay, that leads us to 3:45. Anybody have any last minute questions? All right, yeah.
Who made LT Spice?
Linear technology.
I thought it was Dr. Baker.